So, let's continue talking about what we've been talking about. We've been talking about the normal distributions. Let's go into writing mode. And that is not what's supposed to be showing up. There we go. Okay, and my camera is all small. What else going on? There we go. I look better. Okay. So, we talked about this last time. The normal distribution is a particular type of continuous distribution, and it has some properties. It's symmetric, it has no outliers, and the measure of center is the mean, and the measure of spread is the standard deviation. Okay, so we talked about this last time. We have a special name for the mean and the standard deviation. They're called parameters. Okay, so you have to remember that the parameters are the pieces of information that you need to completely describe the distribution. Okay, so when we're talking about a normal distribution, we have to write down the two parameters, the mean and the standard deviation. So there are some special symbols for when we're talking about parameters. You use the symbol mu for the mean, and you use the symbol sigma for the standard deviation. You can see it there in green. Okay, so for an example, like you can have a normal distribution with a mean of 3 and a standard deviation of 10. All right, so you would write n comma 3, n parentheses 3 comma 10 end parentheses. Okay. And last time we talked about how, well, what does the mean do? The mean tells you where the center is, in other words, that high point, and then the spread tells you how spread out the distribution is. So if you have a larger spread, we talked about how if you look at the continuous, the graph here, the density curve it's called. So if you look at numbers with a large spread, you can see in red, you have the normal distribution. It's like not very tall and it's very spread out. So larger spreads are shorter and thicker. Okay. Whereas if you look at the one in blue on the left, that has a smaller spread. So it's like everything's gathered near the middle and it's sort of thinner looking. Making sense so far? Okay, so I want to talk to you about like where this, like we end up like using, like where do you end up talking about normal distributions? They actually show up all over the place. So normal distributions show up in many different contexts, in nature in particular. And that doesn't, not everything follows a normal distribution, but a lot of things do. Like for instance, like if you look at the heights of say US adult males, very closely follows a normal distribution. So what does that mean? If you were to look at the heights of US adult males, you would see that it has, if you look at the mean height, that's somewhere near the center if you were like to graph all the information. And you can calculate a spread, and the shape of the histogram would look very much like one of these graphs. And because like we like the normal distribution so much, it's very common to make things a normal distribution. So what does the SAT stand for? Does anyone know? Look at the SAT. Like, what does SAT actually stand for? Yes. SAT. The SAT is an example of a particular type of test which we call standardized. So the people usually think that the S stands for standardized. It's actually scholastic. But the SAT is a standardized test. Okay, now there's another sort of test that people take instead of the SAT. Has anyone ever heard of it? There's another one. Yeah. Okay, cool. I don't remember what ACT stands for, but whatever. But the ACT is also a standardized test. So, does anyone know like what the SAT range is for the scores? Like if you look at SAT scores, like what is the lowest and the highest that you can get? Yeah. And what's the highest? Oh, yeah, 1600, thank you. Used to be out of 2400, but it's out of 1600 now. Now, does anyone know what the ACT score is? Or like what the ranges are? That sounds right. I know it's like in the highest is something in the 30s. So, here's the problem. Let's say that you're like doing college admissions and someone takes the SAT and someone else takes the ACT. Like, how do you compare these two scores? So, like, this is a very common issue. Okay, so it's not letting me type. So, suppose you have SAT and ACT scores. How does one compare them? Interestingly enough, because they're both standardized tests, makes this easy. And we're going to talk about like how that works. Okay, so they're called standardized tests because the scores actually fit a bell curve. Like what they do is, the way they calculate the scores is they give everyone a score so that you get a normal distribution of scores. And it's actually possible to make comparisons between different normal distributions, and we're going to talk about how you can do that. Okay, so the SAT is a normal distribution, and it works like this. The average score is 1100, let's say. And the standard deviation is going to be 200. Let's just rewrite that. The comma makes it look weird. Okay, so the way you would write this is you would say that SAT scores are normally distributed according to, you put n 1100, comma 200. Okay, so what is the typical SAT score in that case? It's like typically what do people get as their score? Yeah, exactly. So that tells you like what normal is. Okay, and if you look at the ACT, it also follows a normal distribution with a mean of 21 and a standard deviation of 6. So we would say that oops, let's put a little comma. So we would say that, oops, there we go. So ACT scores are normally distributed. Oh, we should say distributed, not normally distribution. Normally distributed. So ACT scores are normally distributed according to n 21,6. Okay, so right away you can see that there's two numbers that you can say are the same. So what are the two scores for these two distributions that you know basically are equivalent? Like, what would your guess be? There's two different scores that you're going to say, oh, these scores basically mean the same thing. Yeah, exactly. The typical values are the same because those are both what are typical. So what that's telling you is that if a typical person takes the SAT, you expect them to score somewhere near 1100. If that same person takes the ACT, you expect them to get like a 21. But then you run into problems of like, let's just come up with this. Which score is better? A score of 24 on the ACT, or another number, or 1300 on the SAT. There we go. We'll use those. Okay. Okay, and you can actually answer this. You can figure it out. So there's a formula to do this. Okay, and we call it a z-score. So a z-score allows comparisons between different normal distributions. Okay, and the z-score is special. A z-score is a particular normal distribution. It is a normal distribution with a mean of 0 and a standard deviation of 1. Okay, so the way it works is, let's say you have a normal distribution with some mean and some standard deviation. And you have another distribution with some other mean and some other standard deviation. When you calculate the z-score, it translates everything to the same distribution, which is called the standard normal distribution. So this is called the standard normal distribution. What makes it the standard normal distribution? Well, the mean is 0, and the standard deviation is 1. Okay, so a z-score is basically where you take some number from some normal distribution, and that tells you where it would be in the standard normal distribution. And then you take some number from another distribution, you calculate its z-score, and then that puts it in the standard normal distribution. So that allows you to make a comparison in one place, basically. Okay. And the way you do this is you calculate the z-score, so it works like this. The z-score, so z is equal to the value. That's a value from some standard, from some normal distribution. And you take that value and you subtract the mean from that normal distribution. And then you divide by the standard deviation from that normal distribution. So writing with this with symbols looks like this. Usually we use x to mean the value. And then what's the symbol for the mean? Yep. And then you divide by what's the symbol for the standard deviation? Yep, cool. So this, to calculate your z-score, you take the value for your number, subtract the mean, divide by the standard deviation. Okay, so let's do that. Okay, so what were our two things? I think we had an ACT score of 24, and I think we had an SAT score of 1300. Okay, so remember, for the ACT, the mean was 21, the standard deviation was 6. And then for the SAT, mean of 1100, standard deviation of 200. Okay, so you start calculating everything. Your z-score is going to be the value. That's the number given. So you get a value of 24. Subtract the mean. Divide by the standard deviation. That looks like a couch. And then you do the same thing for the other one. You take your value, which was 1300, that was the score that the person got, subtract the mean, divide by the standard deviation. So you go and calculate this. Let's do the SAT score first. 1300 minus 1100 is 200. and 200 divided by 200 is 1. So that's your z-score. So this is the z-score for an SAT score of 1300. Okay, now you go to the other one. 24 minus 21 is 3. You divide by 6. 3 divided by 6 is 0.5. Okay, so what is this? This is the z-score for an SAT score of 24. So I'm going to pause for a moment. Does it make sense how we calculated these z-scores? Or anything you want to ask, yeah, so far about calculating them? Bueno so far though? Okay. So to compare them, you have to remember that z-scores come from the normal distribution with a mean of 0 and a standard deviation of 1. Oh yeah, sure. Okay, I'm gonna pause. Okay, 1 second. I'm gonna check on my tea. Oh my god, I boiled away 100 milliliters of water. That is sort of nuts. Okay, so you have to remember that the z-scores are a normal distribution where the mean is 0 and the standard deviation is 1. So what I'm going to do is I'm going to draw that. Okay, so here is like the shape of my normal distribution. You just generally draw the ghost shape. Does everyone see how it's symmetric? Okay, now at the high point, where is that, the high point for this normal distribution? Where is that mode? What's the value for it? 0, yes. So that center is 0 because that's what it means. That's what the mean is for a normal distribution. Okay, now what you do is you go and you place the two different numbers on the graph. So remember, for the ACT, the z-score was 0.5, so let's say that's like right here. So I'm putting a little X. That's my z-score for the ACT, which was 0.5. Now, what was the z-score for the SAT score? That was like 1. That's like right there. So the z-score for the SAT score was 1. Okay, so what this is telling you is you can compare these two numbers. Now, for tests, what's better, a higher or lower score? Yeah, exactly. So what that means is that the better test is the one with the higher score. The SAT score of 1300 is better than an ACT score of 24. Okay, you have to pay attention to that. You have to pay attention because does it make sense for some things you prefer a lower score? Like, what's a game where a lower score is better? Like one that's pretty popular in America that I can think of. Oh, yeah, Uno or like golf or something like that, right? So does it make sense you just can't choose the higher number? You need to actually pay attention to like the context of the game. Like if you were to calculate z-scores for golf scores, lower would be better. In which case the 0.5 would win. Okay. So calculating z-scores like this ends up being really useful. I just want to know, like, is this making sense? You calculate the z-scores and then you compare those so that you can like compare contexts, basically. Contexts. There we go. Mucho bueno? Oh, you could not. Did it make sense though eventually when I was talking about like comparing the different scores? Oh yeah. So like for golf, right? Like that's something where you would want a lower score. So then the point. Is that where you are today? I know that feeling. It's okay. We'll talk about other examples of this. Actually, I have a really cool example about like of using the normal distribution. Let me find it really quickly. I want to open this and I want to show it to everyone. Shit, where did it go? 1 second. Go class notes. Old stuff. There we go. This is it. Yes. Download this. Okay, 1 second, I'm just loading it. Okay, this is gonna be so cool. Okay. 20 minutes. Okay. Yeah. So, here, I'm gonna load this. I'm gonna share my screen. Okay, does everyone know what OkCupid is? Yes. Okay, OkCupid is really interesting because they make you share a lot of information. Okay, so one of the things that they make people share is how tall they are. So, let me bring up my annotation. Well, yeah, but we're going to talk about height in particular. So they make you share how tall you are. Okay, now, it's just a fact of life, but when men are talking about how tall they are, what do we think they're more likely to do? Yeah, exactly. So the cool thing is that we actually know that if you look at the heights of adult males in America, the average height is 5'8". And the standard deviation is something like 2 inches. Okay, that means that the typical US adult male is 5'8". The average is what's typical. So like if you look at this like histogram looking thing right here, the density curve, you can see that there's some men who are about as tall, as short as 4'6", and there are some men as tall as 7 feet tall, right? But the fact is that if you draw the curve right in the middle where most men are is about 5'8". That's what's typical. Now, men on OkCupid, where are they coming from? Most of them. Like, what's their place of origin? No, they're coming from America. Yes. So, but we're gonna work through this. So the men on OkCupid are American. So, what should the average height on OkCupid be? Yes, there, excellent. Does it make sense, like, where that train of thought came from? Like, the men on OkCupid are American, which means tall hair counts. Which means that, like, they should have the same average height as America in general. Now, here's the funny thing. This is actually the data from OkCupid, and you can see that the high point for this curve, which is of the heights of men on OkCupid, what does it actually appear to be? Like, what are men saying? What is the typical height on OkCupid? Yeah. So there's two possibilities. Either the men on OkCupid just happen to be taller, you caught in 4K, or what? So the men on OkCupid are taller, or what? Yeah, they're lying. And it's probably that they're lying. And this is like a cool thing that the people on OkCupid were able to do, like, because what's the whole like what's the whole assumption that men say they're how much taller than they actually are? Like, how much do they pad their height with? Yeah, and you can actually see systematically that is what they do. Like, men seem to systematically lie about their height by about 2 inches, and you can see it in the data because we know that the average should be 5'8", but the average ends up being something like 5'10", which is sort of cool. Like you can use the fact that something is normally distributed to like make little inferences like this. Do you think women also lie about their height? They do. And interestingly enough, looking at the data, how do we think women lie about their height? Like, men exaggerate. Like, what do you think women do? Yeah, actually, it's really interesting. When I looked at it, there's actually 2 things that happen. Women are a more complicated story. So, the average height of women in America is like 5'3", I think. It's either 5'3" or 5'4". And what ends up happening is that there's 2 weird little bumps. Average gain. So, women who are average height, they actually say that they're taller. So people who are like 5'4", they usually say that they're like 5'5". Okay, and then there's this other weird thing that happens over here. There are more women who say they are 4'11" than they should. Why is that? Yeah, most women who are like 5'4" or 5'3" say that they're 5'5". They like to say that they're taller than they are. But something else happens at 4'11". Yes! I guess it's a thing for tiny chicks. They're like, I'm not 5 feet tall, I'm 4'11". So like there's this weird like, yeah, 4'11" is just cool. You're like, I'm in the 4 foot gang. And there's another interesting thing where this happens. Guess where it happens? Well, not quite 5'9", wrong number. Yeah. Yeah, for some weird reason, like, well, I guess it sort of makes sense. Like, really tall women are more likely to understate their height as well. So it's like weird. On the edges, women will say that they're shorter than they are, but then like in the middle, they say that they're taller than they are. And I remember I read a blog post written by the people at OkCupid who were like, they were like, why the fuck does this happen? So like someone like wrote like a whole big thing about it. So anyways, like, yeah, there's all sorts of cool shit you can do with this. Yeah, actually, let me bring it up. They used to have this really cool data blog. Let me change my screen share. Let's see if I can find it. Oh no, it's a legit dating site. Then the people who ran it were like, "Holy shit, we have like a ton of data. Like we can, like they write a straight up blog about it." Here. Yeah, they use that whenever all that stuff that you write in there. Like they write these things here. See, look, they even have the OkCupid data blog. So like they go and they look at it. So like they look at people's like political preferences, and they're like, so like they like tracked what people said about how they feel about like homosexual and transgendered people, and then they noticed in the data that people got woke in 2017, or yes, some of your coworkers will hook up at the holiday party. Like they they just go through and they analyze the millions of responses they have, and they just look at stuff like, look, this is a post about office party hookups. How attractive are students at online colleges? Oh, this is really interesting. So they ask they ask people like, are you in school? What sort of school are you in? So they do this whole thing to see like people who are at online schools, like are they more attractive than people who are at like in-person schools? All sorts of cool stuff. So they use all this, all the info they have. Oh, it was a post in 2017 about how one night stands were in high demand, because they also like analyze all the messages that people make. So anyways, really cool. Wait, what? Yeah, exactly. Yeah, they do all sorts of things like that. They're like, because they have access to all the stuff, right? And then they like, if people, because they have, like, there's this little option, like you're supposed to tell them if you like actually met in person. So I guess they go and they look at like all that sort of stuff. So I thought it was pretty cool. They have like a whole blog about it. So yeah, I mean, it's intense. It's interesting. You can do all sorts of stuff with data. But let's go back to the normal distribution. So I wanted to... Okay, so there's another thing I want to talk to you about. So with the normal distribution, there's something called the empirical rule. And it's one of the reasons that we like dealing with normal distributions. So let me draw a picture to explain, like, what is this empirical rule? So let's say you have a normal distribution, and you have some mean, which we're just going to call mu, and you have some standard deviation, which we're just going to call sigma. Okay, so there's my normal distribution. What's the value right here in the middle? Mu. Cool. Now, we're going to use the standard deviation. So I'm going to mark on here mu plus sigma. So what this number is I took the mean and then I added the standard deviation to it. Now, I can add the standard deviation to the mean, or I can subtract the standard deviation from the mean. So that's going to be equal to mu minus sigma. So let's look at this with an example. Let's say you're looking at men. We know that their mean is 5'8". And let's say that their standard deviation is 2 inches. So I'm going to draw my graph. Okay, so what do I have right here in the middle? What's that number going to be? 5'8". Okay, and if I go one standard deviation to the right, where do I end up? No. $5.10. Because if you start it, because it's 2 inches, right? Okay, and if I go one standard deviation to the left, where do I end up? Cool, thank you. Yes. Okay, any height between those two numbers is said to be within one standard deviation. So we would write, let's write it right here, any height between 5'6" and 5'10" is said to be within one standard deviation of the mean. So in other words, if your height is like anywhere in that region between 5'6" and 5'10", that's within one standard deviation of the mean. In other words, this blue section of the graph right here. Okay. Now you can go out another standard deviation. And what that would be is mu plus 2 sigma or mu minus 2 sigma. Now for our height example, if you got one more standard deviation to the right, you are at 5'10". If you add 2 more inches, you're at 5'12", which is 6 feet tall. Now if you're at 5'6" and you go another standard deviation to the left, that's going to put you at 5'4". So we would say that any height between 5'4" and 6 feet tall is within 2 standard deviations of the mean. Okay, and you can go out one more time. So if you go out another time, that's going to be mu plus 3 sigma. If you go out another time, it's going to be mu minus 3 sigma. So for our height example, you start at 6 feet tall and you go out 2 more inches. It's going to put you at 6'2". If you start at 5'4" and you go out another 2 inches, that's going to put you at 5'2". I think I'm probably wrong actually about that that's what the heights are, but whatever. Just assume that it was 2 inches. Actually, I'm going to quickly Google it because I wonder what the right height was supposed to be. Yeah, apparently the standard deviation is actually 3 inches, but whatever, we'll just use 2 inches. Okay, so what can you say about if the height's between 5'2" and the height's between 6'2"? Any height between 5'2" and 6'2" is within 3 standard deviations of the mean. So what I'm wondering at this point, is it making sense? Like, if I was to say, oh, it's within 3 standard deviations. Do you get how to calculate that? You start at the mean and you go out by the amount of the standard deviation. Yes? No? Okay. Wait, how did I get 3? Oh, so let's just like walk through it here. You start at the mean. To get 3, you add 1, you add 2, and then you add 3 standard deviations. So to get out to here, you have to have added 3 standard deviations. Or you start at the mean and you subtract 1, you subtract 2, you subtract 3 standard deviations. So do you see how I'm going in jumps of 1 standard deviation at a time? So the empirical rule is actually going to tell you what percentage of people are within these different categories. So fun fact, approximately 68% of the population is within 1 standard deviation of the mean. So what does that mean for height? 68% of men are in what range of height? They're between what two heights? Yes. And we keep going. The empirical rule tells us that approximately 95% of the population is within 2 standard deviations of the mean, which means that 95% of men are between what two heights? Not 5'2" and 5'6". 5'2" and 6'2" was 3. So you gotta look. Go. Yes. And finally, approximately 99.7% of the population is within 3 standard deviations of the mean, which means 99.7% of men are between what two heights? 5'2" and 6'2". So why do we not go past 3 standard deviations? Is a good question. Why not have a 4th standard deviation? Rule here in percentage. Well, you can't go over 100%, but how much is left over is a good question. Yeah, does it make sense that 99.7% is basically 100%, right? And that's, I assume, what you meant by that, like, because you can't literally go over 100%, but, like, yeah, how much more is there to even capture? So it's basically everyone. So one of the consequences of this is that 3 standard deviation, or 3 sigma, is basically everyone. Like, obviously you have that 0.3% left over, but I mean that's not a lot. Does that sort of make sense? Like, you're like, whatever, I'm just gonna cut it off there, like it's basically everyone. Yes. Yes. It's always 68%, it's always 95%, it's always 99.7%. And in fact, this is the empirical rule. Another name for it is the 68, 95, 99 rule. Right? Just because the numbers are always the same. So actually, I'm going to quickly Google the info about women. So women, US, height, standard deviation. Let's see how much longer do we have? Okay, we have. What time did we go to? Oh, 2:15. Okay, we go. Okay, so apparently women, their heights are a normal distribution where the mean is 64.5 inches and the standard deviation is 2.5 inches. So let's convert that. 64.5, 5 times 12 is 60. So that's, okay, yeah, women are basically 5'4" on average. 5'4.5". And let's round the 2.5 up to 3. Okay, so what you could do is you can draw your little normal distribution curve. And now you can start making some claims. Well, right here in the middle, that's going to be 5'4". And then you can start moving one standard deviation at a time. 5'4", if you add the 3 inches, because we rounded up, we're going to use this one, you're going to get to 5'7". And then you can go another 3 inches. That's going to be 5'10". And then you can go another 3 inches, 6'1". Okay, so why am I stopping here? Right, but there's a reason for that. Like, what do you know about 3 standard deviations in terms of the population? Yeah, exactly. So, does anyone here know a woman who's taller than 6'1", out of curiosity? How many people here know someone who's taller, a woman in particular, who's taller than 6'1"? Like, it's pretty rare, right? Like, you're a pretty tall woman if you're taller than 6'1". It's just facts. So, like, using the empirical rule, we know that most women we encounter are probably not going to be taller than 6'1". Does that mean there aren't? No, but they're a small part of the population. Yeah, the tallest girl you know is 5'9". So let's go the other direction. If you go one standard deviation to the left, 5'4" minus 3 inches is 5'1". You go another standard deviation to the left, 5'1" minus 3 inches is 4'10". And you go one more standard deviation to the left, and you're at 4'7". Does anyone here know a woman, a grown-ass woman, who's shorter than 4'7"? Okay, one person. Anyone else? Out of curiosity? No, but okay. So, but apparently, this person that you know is very unusual. Okay, so like remember, this goes to like everyone in here. This is basically everyone between 4'7" and 6'1". That's basically all women. Now, the basically, you know, what percentage actually is this? What percentage of women are between 4'7" and 6'1" according to our numbers? Yeah, not 97, 99.7. Okay, which means, like, how many women do we have out? What percentage of women are going to be out past 6'1" and out past 4'7"? Like, shorter than 4'7" and taller than 6'1". Like, what is left over for them? Like, what percentage of women are going to be in total in either of those categories? 0.3%. Which means, actually, what percentage of women are going to be taller than 6'1"? If together they make 0.3%, what percentage of women are just taller than 6'1"? Yeah. 0.15% of women. What percentage of women are going to be taller than 4'7"? 0.15% of women. So like, let's say that you're like a height fetishist, and you're like, do you know what? I just want a tall chick. She has to be taller than 6'1". What percentage of women are going to be available to you? Like roughly 0.1%. Or let's say you go the other way and you're like, I just want a really, really short woman. She's got to be shorter than 4'7". You're basically like restricting yourself to like 0.15% of women in America, at least. Some other countries, you know, they have shorter or taller averages. So anyways, like it becomes a real numbers game here. Okay. So is this making sense so far? What you can do here with this? You get some ideas of like what percentage of people are in whatever range. Anything we want to ask? I think we're gonna just end here today. So I'm just gonna stop the recording.